dissociates. Our strong electrolytes may completely dissociate. What does that mean? Let's take a look at an example. Let's say we start off, we have 1 mole of HCl, okay? You put it into water, right? Strong acid, I'll put it this way, I'll put initial concentrations here, okay? And this here, Na, there's more than enough, okay, 1 mole, and then 0 and 0 for these. All right? So this starting out, initial. Now you put the HCl and H2O, what happens? Final, like I said, strong electrolyte, strong acid, it all goes over there. So there's 0 moles left here. It all went to the product side. And you end up with 1 mole and 1 mole. Okay, is what you have. That's a strong acid. This technically wouldn't be 0. It'd be some super, super, super small number, but so small that we consider it 0. Strong acid all goes to the product side. Okay? Now I could probably imagine a weak acid only partially disassociates. It all doesn't go to the product side. Let's look at that. Weak acids are weak electrolytes. They only partially dissociate. Okay, let's take a look at an example. Let's take a look at hydrofluoric acid as a weak acid. Again, hydrogen is going to, HF is going to donate its proton to the water. Like so. Okay, again, we're going to have initial we're going to start off. Again, say we have 1 mole here, and we have 0 moles of each one of these. Right? Now you put the HF into the water. Now HF is a weak acid, so it's only going to partially dissociate. And actually, we can calculate this out. We'll learn how to calculate this out in the next chapter. But we're going to have final. We're going to have something, and I'm making up these numbers. We could actually calculate them out, right? But we're not going to calculate them out right now. Instead, what's going to happen is you're going to have a 0.9 moles here, and 0.1 moles will go over here. Now again, we can actually calculate these numbers out. I'm just making them up. But the point here is just to show you that this is a weak acid. It only partially disassociates. Okay? That's all I'm trying to show, all right? A strong acid completely disassociates, all right? We also have strong bases and weak bases, which would be similar, right? But they're not as important as this, okay? Hopefully I explained that so it makes some sense. And actually I goofed up here. Should have a two-way arrow, okay? There should be a two-way arrow because it's a reversible equilibrium. It's dynamic equilibrium. Okay, you have some going in the forward direction, some going in the reverse direction. Now remember we had K equilibrium, or KC, right? From I don't know how many chapters ago. Well, we're going to have that for weak acids, okay? And it's called the acid dissociation constant. But it's related to K equilibrium, right? I'll put it this way. K equilibrium for acids, okay? Again, it's going to be capital Ka. It's going to be similar to K equilibrium, Kc or Kp, Ka, and this is called the acid dissociation constant. All right? Now let's take a look at a generic example. We're going to have our weak acid, Ha, plus our water. That's going to go reversibly, right, to H3O plus A minus, right? So A is our, HA is our acid, right? This is our base. Proton gets transferred to the H2O, making the H3O plus hydronium ion, and then we end up with A minus, okay? Our conjugate base, right? This would be conjugate acid, conjugate base. So we can write K equilibrium for this thing. Again, it's called Ka for an acid, right? How did we write that? Products over reactants raised to their stoichiometric coefficients. So we're going to have Ka, right? Products concentration, we're talking about the molarity, divided by the concentration of the reactants. What did we have for that? We did not include liquids and solids, correct? So we're just going to have HA. Like that. Okay, again, acid dissociation constant, right? Nothing new really, okay? It's just K equilibrium, except we applied it to an acid. That's all we did, right? Now, we can imagine if we have a stronger acid, as our acid strength grows, what's going to happen? You're going to have more and more and more products, right? If your acid is stronger, what's your more products, what's going to happen to your numerator? It's going to be larger. This will be smaller. So basically, long story short, what am I trying to say? The larger the Ka, the stronger the acid. The larger the Ka, the stronger the acid. All right, long story short. If you have a strong acid, your Ka is much greater, going to be much greater than 1. Much, much greater than 1. It's like for hydrochloric acid, nitric acid, sulfuric acid, all of those, okay? Again, all the acid is going to be on this side, right? You end up with a very large Ka. Again, normally I'd ask if there are any questions, but I'm going to stop this video there right now.